Hello, everyone. Thank you so much for introducing me. So my name is Dilawer Ahmed, and I'm from North Carolina State University, and today I'll be presenting our work. Our work is on voice command fingerprinting. In a voice command fingerprinting attack, the goal is to identify what the user is using the voice assistant for, or what activity is being performed on the voice assistant. This is an example of a privacy attack which can result in sensitive information about user being leaked, such as maybe your political affiliation or your home occupancy status, among other things. And this attack is classified as a purely passive attack using sniffed encrypted network traffic. So here's how a typical voice assistant works. You have a user they say the wake word followed by a request. The speaker records this, sends this over the network. It's forwarded to the backend requested server. The server then processes this request. This step may include some backend server-to-server communication, but it finally responds, and the response is sent all the way back to the speaker, which then responds with the appropriate thing to say. But in a voice command fingerprinting attack, you have an attacker that is snooping on this link between the router and the internet, and the workflow remains the same, except when the attacker gets the packet, it silently makes a copy of it and forwards the original packet back. And afterwards, it does the same thing with the response as well. And then the attacker can then use this copied traffic to process and then find out what the command that was being said to the voice assistant. It seems simple enough, but when you consider an attacker that's outside the local network, there are a few challenges that come with it. First of all, there is no straightforward way to know when in time the voice assistant was used. And second, due to network address translation on the router, traffic from multiple devices or other devices on the same network is not easy to separate from each other. To tackle these issues, we split our attack into two components, first of which we call invocation detection, which detects when the voice assistant was used, and then activity detection, which basically detects what the activity was. And we also introduce traffic flow filtering to basically filter traffic from other devices on the network as well. So what is invocation detection? It refers to, or it answers the question of, was the voice assistant just used for the adversary? And from the adversary's perspective, there are a couple of properties that they would like the system to have. One of them is continuous real-time detection, so that they don't miss any invocation. Second one is low or no false positives, so that they're not bombarded with false alarms. And third one is lightweight, so that they don't have to use or waste any resources. In the activity detection, it answers the question, what was the voice assistant used for? And this component needs to focus on being more accurate rather than being fast. And it should be able to capture weighted commands. For example, if I ask my voice assistant to open my morning workout routine, or ask my morning workout routine to start my workout, it should still be able to tell that I'm essentially saying the same thing with different phrases. And it should also be resistant to noise. As I said, traffic from other devices, from your phones on your laptops, will also be sending out at the same time. So it needs to be resistant to that. To illustrate how invocation detection works, we can consider the simple example. On x-axis, we have time, and on the y-axis, we have the network traffic volume. And let's say at this particular time, we have an invocation. So we consider a window of time around that invocation. And in our case, we considered a width of 4 seconds. We considered multiple different window sizes from 2 all the way to 10. And we found, based on multiple trade-offs, that 4 seconds was the optimal one. And we basically capture traffic from this window, and we slide it over and capture traffic. And basically, in each of these windows, we then extract features and apply machine learning on them. So why would this work? This works because voice assistants are typically idle throughout the day, and they're not sending very minimal or no traffic. But as soon as you see an invocation, you see a sharp uptake on traffic on particular domains. So you can see that here, for example, for Alexa, there's a sharp uptake in traffic for AVS Alexa domain and the Unagi domain, and similarly for other assistants as well. So we exploit this fact, and we exploit this pattern to detect invocation by using the volume of traffic on these particular domains. We compared multiple different machine learning models, lightweight machine learning models such as k-nearest neighbors, random forest, AraBoost, and we found random forest to be overall the best balance between performance and time to predict. And as you can see with the table that it's very, very easy in most cases to detect invocation and activation without much effort. So coming on to activity detection, we can have the same example with the same invocation time, but now we have correctly guessed the invocation time, right? So we can use this, use this intuition, and intuitively any traffic that is related to this voice command should follow the invocation and should not be active before or after a set time after this. So we consider again a larger window size starting at the invocation and ending about 1 minute after. Again, we evaluated multiple different window sizes, and there were trade-offs for each of them, but we found that 1 minute was overall the optimal one for our case. However, the traffic in that window can still potentially contains large amounts of noise because the home network has other devices active at the same time, and that noise can lead to a degradation in performance. So we need to filter out the unnecessary background noise traffic. So we created this flow filtering mechanism, which works on the same intuition that any flow related to the voice assistant should start in a set window after the invocation, and any flow that's active before that or any flow that becomes active after a set time is not related. So we set a threshold-based m-second window for inclusion of flows. So as you can see here, flow 1, 2, and 3 are not included in our approach because they start before the invocation, and flow 4, 6, and 7 are included because they start within the m-second window, and flow 5 is not included because it starts after that. There is one exception though, because voice assistants sometimes also send traffic on flows which are active already. For example, keep live connections and status updates and that sort of stuff. So we need to include traffic from those flows as well. And based on our training data, we figure out what these domains are, and we always include them in the selected traffic. So comparing across platforms, we observed an overall good accuracy with slightly better results for Google Assistant and Siri, but we see in the overall we get a good accuracy for all assistants. And comparing across different command types, we saw that we have a very high accuracy for streaming commands, but for performance suffers slightly for simple commands and skills. To understand why the performance was suffering, we did further analysis, and we found that most of these errors were either due to similar commands. So for example, if you ask the assistant add milk to my shopping cart versus add bananas to my shopping cart, it was often mistaking it for each other. A case probably can be made that these commands are essentially just interacting with your shopping list, so our high-level activity is the same, but nonetheless, that was the source of most of our errors. And the second source of error was the skills from similar functionality from the same vendor. So for example, rain sounds and ocean sounds both play sound over your voice assistants for you to sleep better. So finally, we built an end-to-end classification system. We combined all these components, and we start from the network traffic. We use the network traffic of 4 seconds to detect invocation. If we don't detect an invocation, we simply go back and start the next iteration. However, if we do detect an invocation, we then invoke our flow filtering component, which takes more traffic from the network and can essentially flow filter to be used for activity detection. We can also optionally add an open world detection to detect commands that were not part of the monitored set or are unknown to the classification to avoid them. And if they are known, we proceed with the activity detection. And if they are unknown, we simply go back from network traffic to start the next iteration. Finally, the activity detection outputs a label, and after outputting the label, it also goes back for the next iteration. So we conducted an IRB-approved study with across 5 days with 15 participants. We had a 1-hour session each day with 3 participants each. We used the Alexa assistant for this study, and we used our pre-trained invocation detection and activity detection models. The participants in the study were assigned devices such as laptops, smartphones, and smart TVs. And the idea was for them to continuously generate high amounts of background noise traffic. And they were also asked approximately every 2 to 3 minutes to invoke the voice assistants as well. And we wanted to see if, in the presence of all that traffic, can we still detect the invocations. And we found that all invocations were correctly detected without any false positives. that means 100% accuracy. We had a 91% precision and 92% recall in distinguishing novel unknown commands. So these would be commands that we were not considering in our set. And we had a 77% overall end-to-end accuracy in detecting voice commands. So this shows that this attack can practically be carried out in the real world as well. However, our work suffers from some limitations. First of all, we can't fingerprint two same platform voice assistants that are active within 1 minute or within a set time that we set the window of at each other, because we're already in the end-to-end process when that comes in, so we won't be able to detect its invocation. And we only focus on about 100 commands set at the same time. A case can be made that you can focus on privacy-sensitive commands or what the commands that you're really interested in, but increasing this command to above this threshold might be interesting for future work. And our domains for invocation detection are region-specific and would need manual work for selection in other regions. So for example, unagi.na.amazon.com is specific to the North American region, and for European or Asian regions, these domains might be a bit different. So coming on to our contributions, we focused on fingerprinting the top 3 most popular voice assistant platforms. We introduced flow filtering and invocation detection. We improved the state-of-the-art accuracy in voice command fingerprinting with using multiple types of commands such as skills and streaming commands. We designed an end-to-end fingerprinting method, and all of our code and data is open sourced. And I'd be happy to take any questions if you have it at this point.